Hello, this is video 2.1 in the fluids unit. So it's the first video for the dynamics portion of fluids. And the essential question for this video is, what are the characteristics of a fluid system? So the first thing we need to do is define what a fluid system is. A fluid system is any single body of continuously connected fluid. That will be considered a closed fluid system. So in the last unit, we were dealing with closed fluid systems, but now we're going to have more complex ones, like, for example, the human body, right? We're a system of veins and arteries, but they're all connected to each other. The fluid in one place is connected to the fluid in other places. Reservoirs, the water pipes in your house are an example of a complicated fluid system. Rivers and lakes could be examples, although if it went over a waterfall, it wouldn't be anymore, because anytime we can get air in between, then we've got separate fluid systems. So they have to be continuous and connected. One of the neat things is that the conservation principles that you learned your freshman year in physics are really the key ideas for understanding fluid dynamic systems. Basically, the simple idea is that mass and energy are conserved when we have closed systems. What that means for a fluid system are, we can't have any leaks, okay, because then mass wouldn't be kept in the system if we want to consider it closed. We can't have precipitation, so rain flowing into the system. We can't have evaporation of water out of the system. We're also not allowed to have any pumps, because that would provide energy into the system. We need to keep the energy in the system conserved. We can't have heat sources that are warming up our fluid, or we wouldn't be able to use some of the equations and things that we're going to derive. So we're considering simple fluid systems in which mass and energy are conserved. So you may recall that fluid dynamics refers to the movement of fluids inside of a closed fluid system. What causes fluids to move in a system? Well, fluids are actually going to move spontaneously. That means they move on their own inside closed systems in order to evenly distribute the mass and energy in the system. This is known as an idea called entropy, which we'll talk a little bit more about when we get to thermodynamics. But for now, I'm just going to start seeding this idea that entropy is always increasing in the universe. It's another fundamental tenet of physics. But distribution of stuff evenly throughout systems is just sort of how nature wants to work. And that's what happens inside closed fluid systems as well. So for example, you may have seen weather maps at some point in your science career, right? If we have a high pressure system and a low pressure system, what happens is the fluid, the air, is going to spontaneously on its own move from the high pressure system to the low pressure system. This is what causes weather. And it's doing that so it can evenly distribute the mass and the energy. So there's going to be two equations that we're going to be deriving in our fluid dynamic unit. One is very simple, straightforward, and then the other one is really complicated. Good news is we're starting with your easy one first. This is known as the continuity principle, aka the junction rule. And there's actually several junction rules in physics, but this is one that applies to fluids. So the rule is that as fluid moves around inside a system, mass and volume of the fluid are conserved. Which means that the mass and the volume flow rate of the fluid into a location or a junction is the same as the mass flow rate out to conserve mass. This assumption, by the way, assumes that fluids are incompressible, which means that we can't squish the volume of the fluid, which is pretty much true for liquids. Gases actually are compressible, and so they end up being a little bit more challenging to manage. But in any case, we're going to make the assumption that every fluid has a constant density and is incompressible. That was a kind of complicated definition, but I think practically you guys will see it works really easy. If I've got 4 kilograms per second of water going in a pipe, and that pipe splits into 2 pipes, and we know that 3 kilograms every second of water coming out of that top pipe, hopefully you could predict that 1 kilogram per second of water is coming out of the bottom pipe. We're not allowed to lose any water in our system. So if we shove a certain amount of mass into a junction, the same amount of mass every second, or mass flow rate, is going to come out of the other end. Incidentally, 1 kilogram of water has a volume of almost exactly 1 meter. So you can go back and forth between mass flow rate and volume flow rate really easily. I could have rewritten this slide, and instead of saying 4 kilograms per second, I could have said 4 liters every second went in, and then 3 liters every second come out of the top, and 1 liter go out the bottom. So both mass flow rate and volume flow rate are going to be conserved in a junction. Okay, so what if we have a pipe that has changing surface area? So like blood vessels in your body that might narrow or get larger. What is going to happen to that fluid as it goes through those areas that have smaller or larger surface areas? Well, if we consider a chunk of fluid that is filling that container, let's say this yellow chunk of fluid at location 1, as it moves through the container, we know that the mass and volume flow rate of that chunk of fluid have to be conserved. So when that fluid moves to the narrower portion of this pipe, location 2, right, instead of being a fat, thin slice of this pipe, it's now going to be a much longer, narrower slice of the pipe so that we can fit the same amount of mass through the pipe no matter what location it's in. What this means essentially is that the larger the surface area of the pipe, the smaller the velocity of the fluid, because in this first area, that water or whatever it is only has to move a very small distance in a certain amount of time to cover the mass flow rate conservation principle. And that means that the velocity of the fluid in that really big area is going to be very slow. When that piece of fluid moves into the other location of the pipe, right, where we have a much smaller surface area, that little chunk of fluid has to get squished and stretched, and in order to do that, it's got to cover a much bigger distance every second, and that translates into a much higher velocity of the fluid. This should be pretty intuitive to you. You've probably done this with hoses before, right? When you turn the hose on and it's got a relatively big diameter, water comes out of it pretty slowly. If you take your thumb and you cover the end of the hose so that the diameter is much smaller, we got to get the same amount of water out of that hose, and it has to come a lot faster in order to get out of the hose. But one thing that's worth mentioning explicitly is that while mass and volume are conserved, velocity is not a conserved property in physics ever, 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 right? So I would never say that the speed in the pipe is constant. The velocity is constantly changing, and that doesn't violate any conservation principle as long as the mass and the volume flow rate are conserved. Okay, so from these ideas of these relationships between the area of the pipe and the velocity of the fluid, we derive this equation known as the continuity equation. It basically comes from the fact that there is an inverse relationship between the surface area of the pipe and the average fluid velocity of the pipe at any location. So this is the way the equation looks, and you may not be able to see that that's an inverse relationship as we kind of described, but if you think of this equation as like a meter stick that has to be balanced on both sides, right? If you have one side of the equation where we have a really big area, okay, and the other side, the area is smaller, well, the velocity on this side is going to have to be small, and the velocity on this side is going to have to be big. So that's how you can always see a big area always pairs with a small velocity, a small area always pairs with a big velocity, so that we can keep this equation balanced. One example of this that you may have seen in your world is just when you turn on the faucet at your sink and you watch that stream of water as it flows. You may have noticed that the stream of water actually changes diameter as it flows, and it's all an application of the continuity equation. When the velocity of the water, when the water first comes out of the pipe, it's actually moving slowly because it hasn't started speeding up as it falls. So it's got a small velocity, and that means that the water stream actually has a larger diameter at that location. And as that water speeds up as it falls, the diameter of the water stream is going to decrease because the velocity is increasing. If you haven't noticed this before, I'd advise you to go turn on your water and take a look. It's pretty cool. So a nuance, a mathematical nuance that sort of catches people in a lot of these continuity problems, because they're pretty simple conceptually, but mathematically, one of the challenges is that they don't usually measure the surface area of a pipe. You don't buy a pipe at a store by surface area. What you do is you buy by diameter or by radius. And the area of the pipe is a function of radius squared, right? We've got that pi r squared radius equation. So when you double the radius of a pipe of any type, whether it's circular, square, whatever the cross-sectional area is, you're actually quadrupling the surface area. You can see that in these rectangles that I've drawn, right? So this is R, and this is basically 2R. And if I wanted to know the area of these pipes, this would be R times R, which is R squared, and this is 2R times 2R, which is 4R squared, right? So this area here is 4 times as big as this area, even though we just doubled the radius. So for example, we'll see how you kind of apply this in a problem. If you are told water flows through a pipe that abruptly triples in diameter, how are the mass flow rate and the velocity of the water in that pipe impacted? So I have this pipe where we've got water flowing in, and then we triple in radius or triple in diameter, which does the same thing. And I want to know what's going to happen to the mass flow rate and the velocity of the water. Well, the first thing is mass is conserved, so the mass flow rate is going to be unaffected. The mass that goes into this pipe is going to be the same as the mass that comes out of this pipe every single second. Otherwise, we're violating conservation of mass. However, the velocity is not a conserved property, and that's going to be different on the input and the output of this pipe. When we triple the diameter, we're actually non-tupling or 9-timesing the area of the pipe, which means based on the continuity equation, the velocity is going to go down to 1/9 of what it was before. So it's not a third like you might think when you triple the diameter. The velocity actually goes down even more than that. If you want to follow through that mathematically, the area of the pipe in that first location is pi r squared because it's a circular cross section. In the second area, we've got pi times 3r squared because we have triple the radius, and that actually simplifies to 9 pi r squared. Then if we substitute in just with variables into our continuity equation, a1 v1 equals a2 v2, on the left side of the pipe we have pi r squared v1 equals 9 pi r squared v2, and then when you cancel out the pi r squared, you're left with v1 equals 9 times v2. So my velocity in on this side is 9 times the velocity that comes out of this side, right? And that tells me that it's going much faster in the small side than it is coming out the large side, which should also make logical, intuitive sense if you kind of think about your experience with hoses. Okay, we've come to an end of this slideshow, but I want to take a minute and revisit the essential question, which is what are the characteristics of a fluid system? And hopefully you understand where the continuity equation came from and also how to use it. Thanks for watching.